This video is not for the faint of heart. Today I'm going to be showing you how to code a neural network using low-level TensorFlow. That's right, no Keras, no special high-level APIs, low-level TensorFlow coming up. Alright, so we are going to be coding a neural network using low-level TensorFlow. We're not going to be using any libraries like Keras or anything like that. So let's get started. So first thing let's do is let's go over our import statements. I've already added them to our script here. We have obviously import TensorFlow, import NumPy, import pandas. Pandas is so we can work with our data. NumPy is, I'm assuming you know what NumPy is, right? For matrices and things like that. Now from sklearn, scikit-learn, we're going to import train, test, split. This is so we can split up our data into training and test data, right? So we're going to use a certain portion of our data to train our model, and then we're going to set aside a small portion of our data to test our model and test how good it is. Pre-processing, we're going to import this from scikit-learn. That's so we can normalize our data, right? So we want to make sure all of our features are on the same scale. So what that's going to do is we're going to use this to compress all of our values between 0 and 1. Now the data set we're going to use is image data, so it's going to be pixel data, right? So the values range from 0 to 255. So we're going to compress all that down between 0 and 1, right? You want, when you're training data set, you want to make sure, when you're using training data, you want to make sure it's all on the same scale, right? Okay, great. I have a simple helper function here, which returns our label data, right? The data we're trying to predict, right? The value we're trying to predict. It just returns it as a one-hot array, which is just an array of zeros and ones, all right? So we have a possible 9 values, right? These represent, so the data it's meant to try to train a data set on a self-driving car, right? So if a 1 here means go straight, a 1 here means turn right, a 1 in this position means turn left, and so on. 1 here means brake, right? Yeah, so that's what that represents. And then some of the other values mean go straight and turn left, go straight and turn right. So just so you kind of get the idea there. But that's, yeah, so that's that. Okay. So that's, oh, the other thing, you notice I created a folder here, models, version 1.0 here. We're going to put our model in here. Actually, let's create a new directory. We'll call this version 2.0. This is the directory we are going to save where we're going to save our model after we've trained it. Okay, this file here, this is our autocar main training data set. This is just a saved NumPy array. That's our training data that we're going to use, and then train model. This is the script that we're in right now. All right, so that's the setup. Now let's get started. All right, so the first thing we're going to do is we're going to set up our parameters, right? So these are kind of like the main parameters that we're going to use in our model, or in our TensorFlow script, or Python script here, okay? So first parameter we're going to need, so we'll just put a little comment here, params. We're going to need to declare our data file path, right? Where is our training data? So it's going to be this file here, .numpy, okay? The next thing we're going to need is, where do we want to save our model? Model save file path, and we're going to save it to models, and we're going to call that new folder we created version 2.0. Oops, and we'll just call it version 2.0. Okay, great. The next thing we're going to declare is our hyperparameters, right? This is how many layers we want, how many neurons we want in each layer, what's our learning rate going to be, how many epochs are we going to run. So these are going to be our hyperparams. Okay, so, and layers equals. So now the layers we include in here are only our hidden layers and our output layer, right? We don't need to define our input data, right? That's going to depend on our data set, right? So just in case that wasn't obvious. All right, so we're going to go with a 3-layer neural network. So we're going to say our first hidden layer is going to be 64 neurons. Our second hidden layer is going to be another 64 neurons. These you'll tweak to as you're improving your model, you'll end up tweaking these. And our output layer, it's going to be a set of 9 values. Remember, our one-hot function here returns a set of 9 values. And again, these are steering values. So straight, right, left, straight, back, break, right? Those types of things. Okay, our learning rate equals, we'll start with 0.001, and then epochs. Remember, learning rate, you probably already know this. This is, if you're watching this video, you probably already know a little bit about neural networking, but I'll explain anyway. Learning rate is pretty much how fast do you want to learn, right? How big are the steps you want to take as you're improving your model and updating your weights, right? You can't make it too big because then it could potentially overshoot and your error could start going up. But you can't, if you make it too small, training is going to be slow. So yeah, and epochs, this is how many times, we'll set this to 5, but this is how many times do we want to train on our entire data set, right? So if we have 1,000 records, how many times do we want to process those 1,000 records during training? So we'll start out with 5 just for now. Yeah, okay. Next thing we want to do is we want to load our data. So we'll do load data. So we'll call this train data equals numpy.load, and then we'll pass in our data file path. Now, next thing we want to do is let's keep track of our rows and column count. So our data rows count equals train data.shape 0. That's the first value. That's our shape, right? So rows and columns. So now let's put our columns in a variable. Oh, oops. Calls count equals train data.shape 1, right? The second value, right? Shape is going to return something like this. Rows, calls, right? So the first value is the rows, second value is the columns. That's what this shape function returns. Okay. Next thing is let's set up some variables here. So we're going to need some variables to hold our column headers, okay? Because we're going to end up taking our NumPy array, loading it into a data frame. So we're going to need to, and remember, this is pixel data. So for the column headers, I'm just going to call it x1, x2, x3, x4, x5, right? Because there's going to be thousands of features, thousands of columns, okay? So let's go ahead and do that. We'll use a for loop for that, but first let's set up parameters, create our variables here. So we're going to call this create training data headers, and you'll see why we need to do this later. So our feature columns, an empty array for now, training data calls, empty array, x calls, empty array, y calls, empty array. All right, now, so for index in range, right? So we're going to write a for loop, 0, and we want to do this for every column. So we're going to use our data calls count that we created up there, right? So now, for every column, okay, if I is equal to data calls count minus 1. So if it's the last column, though, we don't want to follow that x1, x2, x3 pattern. We want to label that y, okay? Because that is if it's the last column, that's the number, that's what we're trying to predict, okay? So we'll do training data calls dot append y. 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 And then now we're going to create, so these feature columns, these are going to be TensorFlow objects, okay? So we're going to call, so feature columns dot append tf feature column. It's going to be a numeric column, right? It's pixel data. And we're going to call that y. Okay? So now we're going to create basically a list of TensorFlow feature columns. Okay? But that's the last column. That's the y column. That's our label. So, but for every other column, it's going to be x, right? So we'll call this training data calls dot append x plus string I. Okay, so if each time it loops through, it's going to label the column. It's going to label the column x1, x2, x3, x4, and so on. Okay. Pen, and we're going to do the same thing in here. And again, you'll see where we use all this stuff later. Now we're going to create our feature column. We're going to do the same thing again. We're going to do append our feature columns, our TensorFlow feature column. So we'll call it tf.feature column.numeric column. Same thing. X. Okay, great. Now, next thing we're going to do is we're going to create a data frame. Pandas data frames are very easy to work with. They allow you to add, remove, they allow you to drop columns very easily and really work with the data. They're very easy to work with. So we're going to load all our NumPy data into a Pandas data frame. Call that df data equals pd data frame. Right? The data, data is our trained data. Index, you have to index the values. So just follow along what I'm doing here. This is usually the best way to do it. Doesn't really need much explanation. Okay. Columns. Now, this is where we're going to use our column headers that we created in our for loop above. Okay? We're going to name this training data columns, right? This contains all of our column headers. Okay? So now we can reference them by name. Okay, great. All right, so now we've got our data loaded into a Pandas data frame. The next thing we want to do is normalize that data. Remember, we want to compress all those values to between 0 and 1 because right now it's just raw pixel data. So let's go ahead and do that. So we'll put a comment down here, normalize data. Okay, great. And for this, we're going to use the scikit-learn functions. Okay, so that function is going to be called min max scalar. And what this does is this uses the min and the max values to shrink all those values down and compress them between 0 and 1. Okay, so that equals preprocessing dot min max scalar. That is the function we're going to use. We're going to call these values numpy scaled. That's going to be the name of the variable we put them in. And we're going to put min max scalar dot fit transform. And we're going to pass it our data, our Pandas data frame. So df data xcols. Now, you see this is where we use that other set of column headers that we created in our for loop above. This xcols only contains the x columns. So remember, we're able, by putting this in the data frame, we're able to reference our columns by name. We have a variable that contains all of the names of our feature columns, our x feature columns only, because we only want to normalize our features, right? We don't want to normalize our y, our label. That's the column we're trying to predict. We don't want to normalize that. So that's what we're doing here. Okay? Now, we're going to store our normalized data. We're going to call data frame np scaled. Okay, we're going to store. That's where we're going to store our normalized data, and then we're going to overwrite the data in our data frame, our xcols. We're going to overwrite those with the normalized columns that are saved in df normalized. Okay, now, next thing we want to do is we want to create our train test split, okay? We have our training data, we've normalized it. Next thing we want to do is we want to set aside a portion of that data for training and another smaller portion of that data to validate our model after it's been trained. All right, so we know how good it is, okay? So let's go ahead and do that. All right, so the first thing we're going to want to do is, so we're going to create train, create train test split. Okay, x data equals df data dot drop. We want to drop our y, and the access is going to be 1. That is our column access. We want to drop the entire column, okay? Because x data is just our features. It's just the values we're going to use to try and predict y. All right, and then y data is going to be df data y. That's going to be our y column. So now we've split out our features from our label. Now we're going to go ahead and create our train and test split by using our scikit-learn functions. So x train, x test, y train, y test equals, these are going to be the return values from that function, train test split, train test split, that's the function we imported above, and we're going to pass that x data, y data, test size, right? What percentage do we want to reserve for our test data? So we're going to use 10%, so 0.1, enter it as a decimal. And the random state, I usually just use 99. You don't have to enter it. Random state just ensures it kind of keeps it consistent every time you run the model, so you get consistent results. That's all that does. And you can enter any value you want in there. It just uses it as kind of like a seed value. Okay, great. So now we've created our train test split. All right, the next thing we're going to do is we're going to convert our y data into a one-hot array. Okay, that's that helper function. We're going to use this helper function that we reviewed in the beginning. Okay, so convert y to one-hot array. Okay, so let's go ahead and do that. First thing we're going to do is, though, let's convert our x data back to a NumPy array from a pandas data frame as matrix. Okay, and then now let's do that. Let's convert our y data equals get one hot y data dot as matrix, and then our y test equals get one hot y test dot as matrix, because it expects a NumPy array. Okay, great. Okay, so now we're going to start defining our TensorFlow graph. We're going to start initializing our weights and bias and initializing our parameters x and y. So let's go ahead and start doing that now. So the first thing we're going to do is we're going to initialize our x and y parameters. These are the values that are going to hold our input data and our label data that we've been working with so far. Okay, so let's go ahead and do that. So we'll call initialize params. So x equals TensorFlow dot placeholder. Now the reason why you need to use a placeholder is because when you're working with input data, right, you don't know what size it's going to be, right? One time you're running, you may have 5,000 training records. Next time you might have 4,000. Okay, so that's where you're going to use this TensorFlow placeholder. Okay, and we're going to define the type. It's going to be a tf dot float 32. And now you're going to define the shape. Remember, we don't know how many rows there are going to be, so the rows are going to be none. Okay, and then you're going to define the columns. So you're going to we'll just use xdata dot shape 1. Okay. Now let's define y. Same concept. Tf placeholder. Define the type. Again, float 32. Define the shape. We don't know how many there are going to be, so none. It's just a placeholder. And then we'll use, we could use our layers, right? Remember we defined our variable up here, layers. We know that our y data is going to have a possible 9 values. So we'll just use, we could just use the length of, and then layers, and we could just do -1, right? Because we want the last value. Okay, great. So now the next step, this is an important step. We're going to create our weights, and we need to randomly initialize them. Okay, so let's go ahead and do that. We'll call this random initialize weights. Okay, and we're going to do this. We're going to create a dictionary here, parameters. We'll call it parameters. Oops. Started out, initialize as empty. Okay, and we're going to do this in a for loop. Remember, we're using low-level TensorFlow now, so we have to do all this ourselves. It's not enough to just define how many weights, how many layers and nodes you want. We actually have to create the weights and bias ourselves here. So let's go ahead and do that. So we use a for loop. So we'll go for each layer in range, how many layers do we have, right? So we use the length of nn layers, right? So because we have 3 layers, so we got to do that. Okay, great. So now let's do that. But so if the layer equals 0, right? So if it's the first layer, remember, we need to define it according to our input data, right? So we need to not define it according to, remember, this layer's value only contains our first hidden layer, second hidden layer, and an output layer, not our input layer, right? Our input layer is defined by our data set. Okay, so we're gonna do that separately here. So we're gonna go parameters, and we're gonna give it a name, W for weight, plus, and we're gonna give it a dynamic name here, plus layer. We'll give it a number, right? So so the first layer will be W1, second layer will be W2, right? These are gonna be the names for our weights. Okay, and we'll call it +1. The reason why we're adding 1 here is because it's 0 index. I'd rather start it at W1 instead of W0. That's why I'm doing L+1. Okay, great. Now, that's going to be a TensorFlow variable. And remember, at this step, yes, we're creating it, but we're also going to randomly initialize it at the same time. Okay, so we're going to use the function TensorFlow.randomNormal. Okay, we need to give it a shape. Okay, so we're going to use xdata.shape, right? Which layer are we in? Okay, so we'll use L. And our columns are going to be nn layers L. Okay, so remember, the number of rows is going to be defined by our data, so that's what we're doing here. Okay, and the number of columns, okay, is going to be defined by our layers up here. Okay, great. Okay, next thing we're going to do is you define a standard deviation. Right, it just makes sure that 0.03. This just ensures that the random data it's creating is in a consistent range, basically. Okay. All right. So that is the random normal function. Okay. Now, the next parameter in our variable is going to be a name. So we're going to give it the same name we gave our parameters here. So we'll just copy and paste this. And there you have it. And that's it. Now, the next thing we want to do is, remember, we're going to randomly initialize our weight and our bias. So we'll just copy and paste this down here. And we'll replace this with a B. And we will also replace this with a B. And the shape. So the shape, there's just one column, okay? So we don't need this. There we go. Oops. I think I took out too much. Yeah. There we go. All right, so remember, that's for our first layer, our input layer. But for every other layer, right, if the layer is 0, we're going to do this. But if for every other layer, we just do else. And we're going to copy and paste this. We're going to change this to L-1. Because remember, so this is using our input data, right? But down here, oh, we need to change this to nn layers. I'm sorry. We just want this to be the shape of our previous layer because remember, this weight is going to get multiplied by the output of the previous layer, the activations of the previous layer. Okay, and everything else stays the same. Our bias, yep, everything else stays the same. Great. Okay, so now we've got our weights and bias initialized. All right, the next thing we're going to do is we're going to want to define our activation functions. We're going to want to multiply our weights and by our activations and add our bias in, right? We're going to want to do perform these operations, right? So let's go ahead and do that. So we're going to create a few more variables here. This is where we're going to essentially train our model, right? This is where we're going to process our training data, okay? So we'll call this hidden out z. We're going to store our weights times our activations plus our bias. We're going to store those in z values, z variable, okay? And hidden out a. This is where we're going to process our activations, okay? So now we're going to use another for loop to process all the neurons in our layers. So for layer in range, and we'll use the same thing, length layers. But in this time we're going to do -1 because our last layer we're going to process differently. So when we process our hidden layers, we're going to use a ReLU activation function, but for the final layer we're going to want to use a sigmoid activation function. Okay, sigmoid activation functions can predict from a range of values between 0 and 1, whereas a ReLU predicts 0 or 1. Okay, so we're going to process our hidden layers differently than our final layer. Okay. Okay, so again, let's do this. Now, if the layer equals 0, for the first layer, we're going to multiply our weights by our input data, x. So let's go ahead and do that. Our first value in hidden out z. Call this z. Remember, we got to give it a name. And we'll do the same thing we did above. All right, so z1, z2, and so on and so forth. Okay, and it's going to be tf.add because we're going to add our weights times our bias. So we're going to nest these functions. So you'll see what I mean. So tf.add. Okay, first thing we want to do is we're going to want to multiply tf.mate mul x times our weights up here, right? Actually, we can copy and paste this. Is that right? Yeah. Okay, so we're going to want to multiply x times our weights, okay? And then, remember, so that we're nesting this matrix multiplication, but then the next part of the add function, we're going to add our bias. So comma, and we can take our b here, plus our bias. Great. And there we have that. Okay. Now, that's for our first layer, right? The reason why we have this if statement here is because if it's the first layer, we need to multiply by x, our input data. However, for every other layer, we're going to multiply by the activations. Okay? So we can actually copy this for the sake of time. Okay? And we're going to change, instead of x, we're going to multiply by our hidden out, our activation from our previous layer. So that's going to be hidden out a. That's going to be a plus string, not L plus 1, just L because it's the previous layer. Okay. So we want to use the actual index value here. I think that's good. Okay, and then yes, add our bias. That stays the same. No change there. Okay, great. So now, all this is done is giving us our z value, right? Our weights times our activations plus our bias. That's all this is done. Now we need to use our activation function to get the value for our neuron. Okay, so we're gonna actually create hidden out a here. So we're going to process our activation, so we'll call it hidden out a L plus 1. equals TensorFlow.nn. We're going to use a ReLU here, and we're going to pass it z. If none of this makes sense, you might want to go check out my Neural Networking for Dummies series, because that explains all this, right? All the math involved. Yeah. But if you got this far, you probably already know this. But if not, check those videos out. Okay. So z, and which value? String L plus 1. Okay. So we're passing our value we got from here, right, to our ReLU activation function, storing that in our activation parameter here, okay? And now we're doing that for each layer except the last layer. And once we come out of this loop now, we're going to process our final layer, where we're not going to use a ReLU, we're going to use a sigmoid, okay? So we're going to call this y equals TensorFlow.nn.sigmoid. And we're going to do the same idea as above, just multiply by the activations of our previous layer, okay? So that's going to be an adder bias, of course. tf.add matrix multiplication. It's going to be a previous layer, so it's going to be hidden out. Oops. Hidden out. Oops. Hidden A. And remember, this is our final layer. So we'll do this a little differently. We'll just call it the length, and then layers minus 1. Okay, that gives us the final layer. Okay, so that's matrix multiplication. So that, okay. And then we need our weights, of course, right? So parameters, our weight, our final set of weights. Great. And then we want to add our bias. So for this, we just add parameters b, and it's the final b, so we can just copy and paste this. Great. Oh, let me close my string value here, and we're done. Okay, now next thing we're going to do is let's define our loss function here, right? So now we've made our we've computed z, we've computed our activations. Here we've made our prediction, stored it in y. How good was it, right? How do we evaluate whether we were right or wrong, and how wrong we were? Okay, so that's we're gonna use cross entropy. Okay, tf_nn L2 loss. Okay, what is that? It's gonna be, it's just gonna be y minus our actual y. So this is our predicted y here, minus our actual y gives us how far off we were, right? And we'll give it a name equals squared error cost. Great. Now we need to define our optimizer, right? So we've created our we've made our predictions. We've defined how good or bad we were, right? And we know how off we were. Now what? Well, now we need to update our weights, right? We need to tweak our weights to hopefully get better and better and better with each epoch, right? Each time we train. Okay, so let's do that. Okay, we'll define our optimizer equals tf.train. We're going to use gradient descent. So gradient descent optimizer. Okay, we need to pass it a learning rate. That was what we defined up here. So we'll copy and paste this. okay? And we call dot minimize, and we pass it cross entropy, right? It needs to know what it's minimizing, right? What function is gradient descent going to minimize, right? It's trying to minimize our loss, right? It's trying to minimize our error, right? Because we're trying to get better and better at predicting. All right, so the next thing we're going to do is we're going to initialize our variables, right? This is required in order to run TensorFlow, because remember, TensorFlow, nothing runs yet, right? If we were to run this, nothing's going to happen yet. Nothing actually runs until you create a session in TensorFlow and then run that session, right? We're kind of just building out what they call a graph right now, okay? So let's go ahead and do that. Call it initialize TS variable. Okay, so we'll call that initialize equals TF dot global variables initializer. Great. Now, we're going to also create some functions here to kind of evaluate y, right? So you'll see what it is. So let's evaluate our prediction. So we'll call this correct prediction. Oh, sorry. Correct prediction. Oops. Okay. Equals TF dot equal y TF dot round our prediction. So what are we doing here? Well, this round function is saying, remember, we use the sigmoid activation function. So that's gonna predict anything from a range of values between 0 and 1. But remember, our actual values, our y values, are one hot array of zeros or ones. So how can we compare the two, right? How can we do that? Well, we're going to use the round function. So if our sigmoid activation function predicts a value of 0.5 or greater, we're going to automatically push that to a 1. Otherwise, it's going to remain a 0. And the TF equal, that's going to compare our actual labels, what should it have been, versus what we predicted. And we're just bumping up. If it's a 0.5, we're just making it a 1, right? So we can compare, see how accurate we were, right? Because we want to know, basically, if we predict a 0 or 1, we want to know we're yes or no, true or false. Did we get it right or wrong, right? If we didn't do this round function, we left it as the actual sigmoid function, it would never actually exactly predict a 1, right? So they would all be wrong, right? So we that's why we're doing this here. All right, that's all that's doing here. So now let's define an accuracy function, right? So that, okay, we've told it row by row how it knows if it was right or wrong, but now we want an overall accuracy, right? Did we get 95% of them right, 80% of them right, 70% of them right, 50% of them right, right? So let's go ahead and do that. So we'll call that accuracy, right? It's just going to give us one number, equals TF dot reduce mean, TF dot cast, and we're going to pass it correct prediction, right? This is where it's going row by row and comparing them. And the type is TF dot float 32. Great. Now, let's also define a predict function we can use later, TF dot round y hat. Okay, great. Now is where we're going to create our session and run our session, and we're gonna write the code so we can actually run this thing. So call this run session. First thing we're gonna do is we're gonna also want to save our model. Remember, we made that folder. Let's create a model saver. So tf.train.saver. Okay, we'll use that later. Now we need to create a session. Remember, nothing runs until you create and run a session in TensorFlow. Okay, so we'll go with tf.session as, we'll call it sesh for short. We're going to initialize operation. Okay, that's going to initialize everything. So we're going to run our epochs here, right? So for epoch in range, and we're going to use our epochs variable we defined above. So remember, we defined it as 5. So this is going to run this whole thing 5 times. Okay, we're gonna track our cost, our average cost, our average error. Okay, start it out at 0. Cost equals sesh.run. This is where we're gonna pass it our functions up here, our loss function and our optimize function. Okay, TensorFlow is going to run that. Okay, so first we're gonna pass it our optimizer, then we're gonna pass it our cross entropy. Okay, this is how TensorFlow knows to run. See, everything's linked. Okay, everything's tied together. Okay, we pass this to TensorFlow and it runs it. Okay, now, but it needs to know what data. Remember those placeholders we created, X and Y? Now's where we're gonna feed those data, real data that we loaded. Okay, so that's going to be your feed dictionary, it's called. And X we pass first. We're going to pass it X data, comma. Y, we want to pass it our labels. Y data. Okay. Now this is going to return C. It's going to return our cost. Okay. And we're tracking the average cost, so we'll calculate that. Plus equals C divided by just the number of examples, right? It's the average. We want to average it. So how many examples did we process? Okay. Now, we're just going to do some print statements here so we can track our progress as we go and see it print out on the screen. That's all this is going to do. So epoch, oops, epoch, comma, the current epoch, plus 1 because we want to start at, we just want to start at 1. We don't want to start at 0. That's all. It's just a display. It's just for visual progress indicator. That's all it is. And we'll format a string here. Okay. Dot format, and we'll pass it average cost. Right, so it'll tell us what epoch it's on and what the cost is currently. Okay, great. Now we'll print out some accuracy statistics here too. So once it's done training, how accurate was it? Accuracy equals plus string sesh.run accuracy, and we want to pass it for the accuracy test. We want to pass it our test data. That's the smaller portion of our data that we set aside. So X data is going to be X test. Y is going to be Y test, and then we'll oh, let's also save our model. Can't forget that. So we'll call model saver dot save. Want to save the session, and we'll use our model save file path that we defined above, and then we'll print training complete. Okay, great. So now we're done. So now we've written all our code. Hopefully we didn't make any mistakes. Let's go ahead and run this and see what the results are. So we'll run our model. Now let's see what we get. All right, looks like we had an error here. Complaining about our input shape. What did I do wrong? Oh, I see. Okay, yeah. Now input shape. This is going to be, I put L instead of a 1. Yeah, we want the columns, right? It cares about the columns, not the rows. So we're going to use the shape. The second value in that our shape returns is the columns. That's what we need to do there. Okay, great. So let's go ahead and rerun this. Should work now. And our model is running, and it looks like it is successful. And as you can see on the screen, here are our 5 epochs that we defined, and our cost is dropping with each run, and our accuracy was 94%. And training is complete. And as you can come down to this folder here, our version 2, and here is our saved model. So that is low-level TensorFlow. Hope you enjoyed that. All right, so that'll do it. Please don't forget to like, subscribe, and hit the bell. And also check out jamestechtips.com for more BI-related content. And thanks for watching.